Dataset condensation aims to condense a large dataset into a smaller one while maintaining its ability to train a well-performing model, thus reducing the storage cost and training effort in deep learning applications. However, conventional dataset condensation methods are optimization-oriented and condense the dataset by performing gradient or parameter matching, which is computationally intensive even on small datasets and models. Here we propose a novel method based on distribution matching. We identify two important shortcomings of naive distribution matching: imbalanced feature numbers and unvalidated embeddings for distance computation, and address them with three novel techniques: partitioning and expansion augmentation, efficient and enriched model sampling, and class-aware distribution regularization. Dataset condensation aims to solve the problem of data hunger in deep learning, which requires a large amount of data to train a well-performing model. It makes storing, preprocessing and training with large-scale data burdensome. The traditional solution to this problem is coarse set selection, which improves the data efficiency by heuristics or representative samples. However, the heuristics might not be optimal for downstream tasks. The presence of representative samples is not guaranteed. Dataset condensation addressed the problem by learning a small set of condensed synthetic samples such that a deep neural network trained on them obtains similar performance. We have a training dataset T which consists of images X and their corresponding labels Y. We want to obtain a condensed dataset S with a much smaller dataset size. Dataset condensation aims to minimize the following objective. We sample the image X from test set distribution PD, and calculate the losses with the parameters of models trained on T and S respectively. Dataset condensation tries to minimize the difference between the losses on the distribution with theta T and theta S. In other words, DC is maximizing the accuracy of model trained on S by updating the synthetic set. However, directly optimizing the objective is infeasible. Because to obtain theta S, we have to train the model for many steps, and it makes the computation very difficult. The conventional gradient matching requires second-order derivative for condensed set update, which is computationally intensive. Instead, dataset condensation with distribution matching proposes a new solution to condense the dataset by matching feature distribution of two sets using maximum mean discrepancy. Distribution matching first sample model parameter from the feature extractor parameter distribution. Then it updates the synthetic set to minimize the difference between the average feature of real set and synthetic set. Although distribution matching is much more efficient, its performance is far from satisfying. Here we study the shortcomings of previous distribution matching methods to propose a better solution with both higher efficiency and better performance. The first shortcoming of previous distribution matching is the imbalanced number of features between real set and synthetic set. Since T is much larger than S, sometimes we need a very small synthetic set. The sample number of synthetic set is insufficient for distribution estimation. The second problem is the unvalidated embeddings in MMD computation. Instead of carefully designing the mapping functions, DM proposed to use randomly initialized networks to get various embeddings for MMD estimation directly, whose validity has not been verified. Our solution for shortcoming 1 is partitioning and expansion augmentation, as shown in the right figure. To increase the number of features extracted from S without increasing its size, for each image, we first partition it into L times L equal pieces, and then expand each piece to the original size using differentiable augmentation. The differentiable augmentation makes the expansion and partition differentiable for loss backward. For the second shortcoming, unvalidated embedding in distribution matching, we proposed efficient and enriched model sampling. We would like to extend the p theta 0 to p theta t. P theta 0 is the parameter distribution for loss computation in original distribution matching paper. 0 indicates the parameters are sampled from the initialized models. And p theta parentheses t is the union of theta distribution with different subscripts. P theta t denotes the parameter distribution of models initialized with p theta 0, and trained for t iterations. And p theta parentheses t consists of all the model parameters at different training iterations. However, the problem for this modification is that collecting parameters for all distributions here is very time-consuming, we need a more efficient way to construct the distribution. Therefore, we propose the memory-efficient model Q, which has 4 operations: push, pop, train and sample. During the training, the Q only includes the parameters in the red circles. The push operation pushes a new parameter initialization to the Q, for example theta n0. The pop operation pops the oldest parameter, which is almost at the end of one row, for example theta 0t out from the Q. The train operation fetches a model from Q, for example theta 1 ton minus 1, and train it for certain steps. Then the parameter moves from t-1 to t, and the final operation, sample, it samples a model from Q for distribution matching. As a result, each row contributes one parameter to the Q. Each element in the Q comes from different initializations and is trained for different number of steps. The push, pop and train periodically update the model Q and add new initialization to the Q to maintain its diversity. The final component of our method is class-aware distribution regularization. We propose to add a classification loss as a regularization term to the synthetic distribution to make the extracted features more distinguishable. Suppose we sample model phi from Q, and we let accuracy phi be its accuracy on real data, and LC be the cross-entropy loss. The regularization term forces the synthetic samples to be classified correctly by the sampled model during distribution matching. All our models are sampled from the model Q and thus have different training iterations. Their classification accuracies vary, and we should only require the synthetic data to achieve the same classification accuracy as the real data. We test our method on 4 different datasets: CIFAR 10 and CIFAR 100, TUE-ImageNet with 200 classes with 64 times 64 resolution images. And the final one, ImageNet subset, contains 100 different classes with 224 times 224 resolution images. For each dataset we test our method on 3 different synthetic set size, 1 image per class, 10 image per class and 50 images per class. Compared to previous methods, our method not only achieves significant improvement over DM but also outperforms other methods by a large margin. Here is the visualization of condensed dataset for CIFAR 10 with 10 images per class. As conclusion, we propose an improved distribution matching method for dataset condensation, and we alleviate 2 important shortcomings of naive distribution matching, achieving significant improvement over previous methods.